talk now about an exciting aircraft system, the lubrication system, and it is exciting because the lubrication oil is the lifeblood of an aircraft engine, and if it doesn't have oil in it, it isn't going to live very long. But the lubricating oil has a lot more functions than just to lubricate in the engine, so let's take a look at what some of those other functions are. In addition to lubricating, the oil seals, it cools, it cleans the engine, it cushions shock, plus it reduces friction, it prevents corrosion, and it prevents metal-to-metal contact of moving parts in the engine. Now, what determines the proper grade of oil to use in any particular aircraft engine? Primarily, it's the operating speeds of the bearings in that engine. Now, in some cases, such as when you have high tooth pressures and high rubbing velocities, and you get these with hypoid gears and similar gears, in some cases, you have to have a special lubricant. You have to use what they call an EP lubricant, and EP stands for an extreme pressure lubricant. So if they say to you on the test that you've got high tooth pressures and high rubbing velocities like you would get with hypoid gears, and what kind of lubricant do you have to have? That means that you need an EP lubricant, an extreme pressure lubricant. Now, for theoretically perfect engine lubrication, ideally what you'd like to have is the thinnest oil that will stay in place and maintain a reasonable film strength. That's what you should use if the other oil requirements can be met in order to get theoretically perfect engine lubrication. And by the way, the thing that has the least effect on the oil consumption of any specific engine is the mechanical efficiency of the engine. Things that do have an effect on oil consumption are things like engine RPM, engine temperature, and so on, but the thing that's got the least effect on it is the mechanical efficiency of that engine. It has the least effect on the oil consumption of the engine. Now let's talk about different types of oil. Aircraft engine lubricants are mineral or synthetic based. They are not vegetable oil based lubricants. They are either mineral or synthetic based, and the reason for that is chemical stability. Chemical stability is the advantage that mineral-based lubricants have over vegetable oil-based lubricants in aircraft engines. Now, if you've got a new reciprocating engine and you're breaking it in, during break-in, what you want to use, what engine manufacturers usually recommend, is straight mineral oil. You want to use straight mineral oil during the break-in period, about 50 hours or so. But after break-in on that reciprocating engine, what most engine manufacturers want you to use then is an ashless dispersant or AD oil, an ashless dispersant or AD oil. Now, why don't you use the AD oil in the first place? Well, the problem with that ashless dispersant oil as far as the break-in period is concerned is it actually lubricates too well for break-in. It doesn't allow enough wear in the engine to properly seat the piston rings, and that's why you want to use the mineral oil for the break-in period about the first 50 hours. Now suppose that the aircraft you're flying has turbine engines on it instead of reciprocating engines. In that case, the type of lubricating oil that you'll almost certainly use is a synthetic lubricating oil. A synthetic lubricating oil like, for instance, Exxon 2380. The advantage of the synthetic lubricating oil is that they have less tendency to produce lacquer or coke. The high temperatures in turbine engines require a real high-performing engine oil, and the synthetic oils, compared to the oils that you would use in a reciprocating engine, have much less tendency to produce lacquer or coke. Now, how about mixing the different types of oils? You cannot do that. The oils that are designed for gas turbine engines and for reciprocating engines are different types with different characteristics and performance capability. You cannot mix those oils. They cannot be used interchangeably. Now, there are some characteristics of oils that the manufacturer uses when he picks what oil he wants in a particular aircraft. You don't have to worry about them as far as picking the oil, but the manufacturer will have been looking at it. One of those characteristics is high flash point. A high flash point is a characteristic to be considered when selecting an engine oil. In other words, how hot does that oil have to get before it can actually ignite? And you want to make sure that it's high enough that the oil itself is not going to start an engine fire. Something else that the manufacturer will be looking at when he picks an oil is the specific gravity of the oil. Now, what is the specific gravity? It is a comparison of that oil, the weight of that substance, to the weight of an equal volume of distilled water at a specific temperature. And the key here is that you have to know that you're comparing the substance, in this case the motor oil, to the weight of distilled water, the same volume of distilled water at a specific temperature. Now, another characteristic of oil is viscosity, and viscosity is a measure of the oil's resistance to flow. And how do you determine viscosity? Well, you determine viscosity by measuring the time in seconds that it takes for exactly 60 cubic centimeters of oil to flow through an accurately calibrated orifice, and it's going to be at a specific temperature. And you need to remember the numbers, that it is 60 cubic centimeters of oil that has to flow through that calibrated orifice at a specific temperature in order to determine the viscosity of the oil. Now, in reciprocating engines, the oil that is used has a relatively high viscosity, and that is because of the large clearances in the engine and the high operating temperatures. High viscosity means that the oil is relatively thick. Temperature is what has the greatest effect on the viscosity of lubricating oil. Cold temperatures tend to make that oil very thick. High temperatures tend to make that oil flow more easily. So temperature has the greatest effect on the viscosity of the lubricating oil. Now, the viscosity index of lubricating oil is based on the rate of change in its viscosity with a change in temperature. So viscosity index is based on the rate of change. In other words, when the temperature goes from one extreme to another, what is the rate of change in the flow of that oil? Lubricating oils with high viscosity index ratings are oils where the viscosity does not change very much with temperature change. So if the oil viscosity does not change very much with temperature change, then that oil has got a high viscosity index rating. Now, here's an oil tank on a turbine engine, and here is the oil filler for that oil tank. It would be nice to know when you're looking at some filler what fluid you're supposed to put in there. So the regulations require that oil tank fillers on turbine engines, or other engines for that matter, have to be marked with the word oil, so that there's not any question about what fluid is supposed to go in that filler. It's marked with the word oil, but you do not have to mark the tank capacity at the filler. The only marking that has to be there is the indication of the fluid that goes in it, which is oil. Now, if you take a close-up view and look inside that oil tank, one of the things you see is that there's an expansion space up at the top of the oil tank. Here's the oil down below, and there's our expansion space. It is required in an engine oil supply tank for oil enlargement in the collection of foam. And how big does that expansion space have to be? It has to be at least 10% of the tank size, or a half gallon. Whichever of those works out to be the larger figure, the expansion space has to be either 10% of the tank size or a half gallon, whichever one is more. And they're going to ask you to work an example of this on the test. So they'll say to you that you have an oil tank with a capacity of 5 gallons. How big does the expansion space have to be? Well, it has to be what percent of the tank capacity? 10% or a half gallon, whichever is larger. If you've got 5 gallons times 10% means that it has to be at least 0.5 gallons. 0.5 gallons is a half a gallon. So either way you look at it here, it works out on this particular tank to be exactly the same. But a half of a gallon is 2 quarts. And that's how the answer is going to be given to you on the test. Not as a half gallon, but in the fact that you have to have an expansion space of 2 quarts. Now let's assume that you've had to make a welded repair to an aluminum oil tank used in any aircraft, but on the test they'll say a turbojet. You need to pressure test that tank, and what do you have to pressure test it to? 5.0 psi. So if you make a welded repair to an aluminum oil tank, you have to pressure check that tank to what psi? You've got it. You check it to 5.0 psi. Now, oil tanks have vent lines, and the whole purpose of those vent lines is to prevent pressure buildup in the tank. The vent line will very commonly go into the engine, particularly in dry sump engine installations, and that allows the oil tank to be vented through the normal engine vent. So it vents it into the engine, and that way it vents through the normal engine vent. Now notice, running right through the middle of this particular oil tank, we've got what basically is an oil tank within an oil tank, the kind of yellowish orange area here, and that's what is called a hopper tank. On the FAA test you'll see it referred to just as the hopper. The purpose of the hopper in the oil supply tank, and not all airplanes have it, not all oil tanks have it, but some do, some don't. When you do have it, the purpose of it is to reduce the time that's required to warm the engine up to operating temperatures. And the way that the hopper tank does that is that basically the oil that is being used primarily by the engine is circulating through this hopper tank area and through the engine, and in normal circumstances, that's the only oil that the engine has to heat up. But all of this other oil is here as available oil supply, and it will be pulled into the line if it's needed. So you've got a lot of oil supply there, but all of this other oil does not have to be heated up when the engine first starts up. All they have to worry about is the oil that's going through the hopper tank itself. So the purpose of the hopper is to separate the circulating oil from the main oil supply, and the reason they do that is to reduce the time required to warm up that engine to operating temperatures. Now, in a turbine engine oil tank, you will often have a dwell chamber or de-aerator. And the purpose of that dwell chamber is to separate the air that is entrained in the oil from the scavenge oil. The scavenge oil is coming in here. Here's your dwell chamber. Here is where the oil goes out to the oil pump. And basically what that dwell chamber is doing is separating the entrained air in the oil from the oil itself in the scavenge oil. Let's take a look now at a diagram of our oil system and talk about some different parts of it. And I'm going to point out the different parts, and then we'll talk about them one by one. Starting over here, kind of on the lower left, we've got the oil line coming in. It would be coming in from the supply tank, and it goes through the supply oil pump, and it goes from there into the oil filter. There is a bypass valve around the oil filter, and there is also in the upper left corner, there is a pressure relief valve, and we're going to talk about all of these as we go along. Now the oil supply pump, in order to keep a constant oil pressure in the engine, of course, as time goes on, will have normal wear, and the clearances between all those moving parts will increase because of normal wear. And the supply pump is going to want to maintain a constant oil pressure. The way it does it is that the output stays relatively constant for a given RPM. The difference is the way that that supply pump keeps the oil pressure stable in the engine is that less oil is being returned to the pump inlet by the relief valve. The oil pump will be putting out more oil, more pressure than the aircraft engine needs. And what will happen then is there is a pressure relief valve here, and it will open and it will let the oil come back into the inlet side of the pump. And as the tolerances in the engine, as the clearances become larger through normal wear, what happens is that the pressure in the engine is less, and therefore the pressure relief valve will not open as wide, and less oil will be returned back to the oil supply pump. So the output will remain relatively constant for a given RPM of that oil supply pump. It's just that less of it is returned by the oil relief valve, by the pressure relief valve. Now, the oil goes out of that oil supply pump and it goes into the filter. This right here is the main oil filter, and there can be various types of oil filters, different ones on different types of aircraft engines. And the main oil filter strains the oil just as it leaves the pressure pump. So you see the oil coming out of the pressure pump, and there is the main oil filter getting it right as it leaves the pressure pump. Now, if you happen to have a Cuno-type filter, if you happen to have a Cuno-type filter, what that basically is it's filtering the oil by wafers that kind of slice the oil and separate out the particles, and the minimum particle size which will be excluded or filtered by a Cuno-type oil filter is determined by the spacer thickness. In other words, how thick are the spacers between the discs that they're using for the filtration. And a Cuno-type filter is also called a stacked disc or edge filtration system, and you'll see those terms also on the test. Now, if you have, like this, a full flow filter on an aircraft engine, in other words, the oil is coming into the filter and flowing clear through it and going out to the aircraft engine, if that oil filter becomes clogged, it's not really going to hurt the engine, because what will happen is there is a bypass valve right here, and that bypass valve will open and it will allow unfiltered oil from the supply pump to proceed on to the aircraft engine. And you say, gee, isn't that a problem? Here I've got unfiltered oil now going to my engine. Well, it's not ideal, but it's a heck of a lot better than not having any oil at all going to the engine. So if the filter becomes blocked for whatever reason, that bypass valve will open and the aircraft engine will still be getting oil. And oil should flow at the normal rate through the oil pressure system. Now, there will be a check valve in the system. Check valve very often is located inside the filter, and the check valve in the reciprocating engine lubrication system is to prevent the oil from the supply tank from seeping into the crankcase when the engine is shut down during inoperative periods, because the supply tank is going to be above the crankcase area, and you don't want that oil to be seeping down and draining down into the crankcase if the engine is shut down. Now, after the oil comes out of the filter, and as it's going on into the engine, you're going to find some last chance oil filters. And the purpose of last chance oil filters is to filter the oil just before it enters the main bearings on the engine. And basically, the purpose of them is exactly what the name says. This is the last chance to get anything out of that oil before it has a chance to clog up the oil jets and basically burn up the bearings in the engine. So that's where the last chance oil filters are, just before the the oil enters the main bearings. Now, as far as the last chance filters in turbine engines are concerned, usually those are cleaned during overhaul, and only during overhaul, because they're so hard to get to, you just can't get to them unless you take the whole engine apart. Now, the primary purpose of changing the engine lubricating oils at predetermined periods is because in spite of all the filters, the oil will eventually become contaminated anyway. And what it becomes contaminated with is moisture, acid, and finely divided solid particles that are suspended in the oil. Okay, we've mentioned in passing, but let's talk about in more detail now, the pressure relief valve that the lubrication system has got. And the pressure relief valve is there to relieve excessive pump pressure in the engine's internal oil system, and that's why they're equipped with that pressure relief valve. Usually, it's located between the pump and the internal oil system. In other words, between the supply pump and the oil as it's going into the engine itself. That oil pressure relief valve can be adjusted to maintain the desired system pressure, so that if you're not getting enough oil pressure, that pressure relief valve can be adjusted to increase the pressure, or it can be adjusted to decrease the pressure. At cruise RPM, you're going to be getting some oil always through the relief valve here of a gear type engine oil pump, and a system that's got the gear type engine oil pump, and that's normal. The relief valve will be set at a pressure that is lower than the capability of that pressure pump. So the pressure pump is going to be putting out more pressure, the supply pump is putting out more pressure than the engine is going to want to accept. That's normal. And so some of the oil is going to be coming back, bypass oil basically. Some of the oil is going to be coming back through that pressure relief valve. And oil is directed then from the pressure relief valve to the inlet side of the oil supply pressure pump. So basically it's just going in a circle here. It's coming through the pressure relief valve and back to the inlet side of that supply pressure pump. The basic oil pressure relief valve setting on a newly overhauled engine is made, where would you guess? In the overhaul shop. When they overhaul the engine, they set the pressure, or that pressure relief valve, at the overhaul shop. Now, if the oil system pressure relief valve sticks in the open position, if that valve opens and sticks in the open position, what do you think is going to happen to the oil in the aircraft engine? Are you going to have too high or too low a pressure? What are you going to have? You're going to have too low a pressure, because then all the oil that wants to, except for restrictions in terms of the size of the lines, is going to be able to flow through that pressure relief valve if it's stuck in the open position, and you're not going to have enough oil pressure, and you're going to have insufficient lubrication. The words the FAA is looking for, insufficient lubrication, is what you're going to get if that pressure relief valve sticks in the open position. Now, one of the things that could cause that pressure relief valve to stick in the open position would be foreign material under the relief valve. And if you do have foreign material under the relief valve, what's that going to cause? It's going to cause a drop in oil pressure, because what will happen is the oil will just keep circulating here rather than building up the pressure like it's supposed to. So if you have a drop in oil pressure, one of the things that can cause it is foreign material stuck under the relief valve. Now, on some larger reciprocating engines, there's a different kind of oil pressure relief valve called a compensating oil pressure relief valve. And the purpose of that kind of oil pressure relief valve is to provide a high engine oil pressure when the oil is cold, and then that compensating oil pressure relief valve will automatically lower the oil pressure when the oil warms up. Now, we're going to talk about the path of the oil inside the engine a little bit more later on when we talk about recips versus turbines. But when the oil gets done doing its lubrication job, we don't want it to all just accumulate in the bottom of the engine. So there will be a scavenger pump. And the scavenger pump, the pumping capacity of that scavenger pump, whose purpose is to take the oil from the bottom of the engine when it's done lubricating and put it back in the supply tank. In a dry sump system, the pumping capacity of the scavenger pump is greater than the capacity of the oil supply pump for a couple of reasons. The scavenge oil is hot, and also it contains air in it, and you don't want the oil to be accumulating at the bottom of the engine. So the pumping capacity of the scavenger pump will be greater, more than the capacity of the oil supply pump. Now, after it comes out of the scavenger pump, the return oil is going to go very often into an oil cooler. Here's our oil cooler on this particular engine. And notice that we've got some lines running around here. Let's assume that the oil line between the scavenger pump and the oil cooler separates. What's going to happen to all that return oil? It's simply going to be pumped overboard if the oil line between the scavenger pump and the oil cooler separates. So let's talk some more about the oil cooler. This is also called, if you want to get kind of highfalutin about it, as they will on the FAA test, the engine oil temperature regulator. The engine oil temperature regulator is the fancy name for the oil cooler, and it's usually, but not always, located between the scavenger pump outlet and the oil storage tank. Now, if you take a look at an inside view of an oil cooler, and they've got different configurations, but this would be pretty typical, here's the way it's going to be working. This is what it would look like if you had pretty warm engine oil going through that oil cooler. And it's coming in over here in the upper left, and it's coming around inside this little jacket area where the orange is, and the valve up here is closed, so it's being forced to go through the center chamber here where we've got a lot of baffles, and this is where the oil is going to be cooled off, and it's going to end up being cooled off the paler yellow here and exiting out the upper right of the oil cooler. So that's the way the oil is going if it's warm. Basically, it's being forced, because this valve up here is closed, to go through the center core of the oil cooler, which is where it gets cooled off, in order to exit and to go on to the return tank. Now, the valve in the upper right corner up here has a lot of names to it. A flow control valve is one of the names that you're going to see, but there are a lot of other names. The bypass valve, the thermostatic valve, the temperature control valve, you're going to see all of those terminologies on the FAA exam. The whole purpose of that flow control valve is to direct the oil through or around the oil cooler. And basically what's happening here is that when the oil is warm, the warm oil heats up this valve, and it expands and shuts off an outlet that would normally be here and forces the oil, instead of just staying in the jacket and exiting to the upper right, forces the oil, because that valve is closed, to go through the core of the oil cooler to get cooled off, and then to exit out as cooled off oil returning to the oil storage tank. And that's the purpose of the flow control valve, bypass valve, thermostatic valve, temperature control valve, whatever name you want to call it, to direct oil either through or around the oil cooler. Now, this is what it looks like if the oil is hot. But what if the oil is cold? If the oil is cold, the flow looks a little bit different. If the oil is cold, what you're seeing then is that the oil is flowing around this jacket, this outer area, which is called, by the way, an annular jacket. It's flowing around the annular jacket, and because this valve, this thermostatic valve in the upper right, is open, that oil will then exit through this area and go on out to the upper right here, and because it's the easiest path for the oil to take, the oil does not go through through the core of the oil cooler, and it doesn't get additional cooling. Doesn't need it. It's already cooler than you want it for the engine. And eventually, as the oil is warmed up, that warmer oil will eventually expand the bellows in this thermostatic valve and close it, and then force the oil to start going through the core of the heater. So the purpose of an oil cooler bypass valve is to direct cold oil directly into the oil supply tank. This bypass valve, when the oil is cold, will be open and allowing the oil to go right out through here and back into the oil supply tank. The temperature control valve, another name for it, is exposed to the oil at the oil cooler inlet. And we're talking basically dry sump reciprocating engines here. So that temperature control valve is exposed to the oil here at the oil cooler inlet. The flow control valve, same valve we're talking about, on the reciprocating engine will open when the temperature of the oil that's returning from the engine is too low. So when you've got cold oil coming around here, that valve will be cold and it will be open, and it will be letting the oil bypass the oil cooler core. So if the engine oil is below normal operating temperature, the oil cooler automatic bypass valve will be open the greatest amount. The more that valve is open, the more compressed it is to the upper right here, the more oil will be able to bypass the core of the cooler and go right on back into the supply tank. Now, what if the thermostatic type oil temperature control valve, this same valve right here, should fail in the open position? What path will the oil take if that valve fails in the open position? If the valve here fails in the open position, is the oil going to go right through the core of the oil cooler, or is it going to go around the jacket and bypass the core? Which one is it going to do? It's going to bypass the radiator core and return to the supply tank if that thermostatic oil temperature control valve fails in the open position. There are a lot of questions, as you can see, about this valve as far as an oil cooler is concerned, and the critical thing you need to be aware of is that if that valve is open, what it means is that the oil is bypassing the core of the cooler, the core of the radiator, and cold oil is going right back into the oil supply tank. Now, let's assume that for some reason the oil has become congealed in a couple of places. Here in the core of the oil cooler, it's all congealed and sticky and nothing's going to be moving through there. But also in the annular or bypass jacket, the oil is also congealed in that area. Now, oil coolers are relatively fragile and relatively thin-walled. If the oil is congealed, the pressure can build up pretty fast. What unit do we have that will protect that oil cooler and prevent damage to it? We've got a valve in the upper left corner here called the surge protection valve. And what happens is that as the pressure builds up in this area right here, it exerts pressure on this spring and closes this valve so that the oil can no longer come around through the annular bypass jacket, cannot go into the core of the oil cooler. Instead, it goes directly from the inlet here immediately to the outlet and completely bypasses all of the tubing and all of the fragile areas of the oil cooler. And that's called the surge protection valve, the surge protection valve. Now, sometimes they have adjustments that control the airflow through the oil cooler, louvers that they can control in order to adjust for how much air is going to be going through that oil cooler. And the unit that controls the louvers to control the airflow is called a floating control thermostat. And the idea behind the floating control thermostat is to control the airflow through the oil cooler so that you maintain a constant normal engine oil temperature. And you need to know that that engine oil temperature should not vary more than approximately 5 to 8 degrees C, 5 to 8 degrees C. And that's the purpose of the floating control thermostat, which controls the airflow through that oil cooler. Now, when you've got some big reciprocating engine aircraft, a Constellation, for instance, if you've got some big reciprocating engine airplanes, you can have a problem due to the quantity of the oil in them with cold weather starting because of the oil getting too thick. And one way to help solve that is an oil dilution system. The whole purpose and idea behind an oil dilution system is that the oil is actually thinned with gasoline, so when you're shutting the aircraft down, so that when you start up the next time, the oil, because as you shut down last time was thinned with the gasoline, is thinner. It will lubricate the engine better. It will start easier in cold weather. If you're going to have an oil dilution system, one of the things you should know about is where the fuel line for that oil dilution system will never be located. It will never be located between the oil pressure pump and the engine pressure system. And the reason for that is that you could end up accidentally, if things didn't work quite right, with oil being forced into the engine fuel system. So the fuel line for the oil dilution system will never be located on the pressure side of the system, of the oil system, between the oil pressure pump and the engine pressure system. It's going to have to be located somewhere else instead. Now, if you've got an engine that's operating with low oil pressure and a high oil temperature, one of the things that can cause that problem is a leaking oil dilution valve. In other words, gasoline is leaking into that oil when you don't want it to be. You've got a leaking oil dilution system that is thinning the oil out, and that gives you low pressure and high temperature. Now, if you're operating with jet aircraft, the oil in a gas turbine engine does not have to be diluted. It is not diluted during cold weather because the engines run hot enough, they have small enough quantities of oil, they just don't need to worry about diluting the oil even in cold weather. Now let's talk about oil pressure for just a minute. The indicated oil pressure of any particular dry sump aircraft engine in normal operation is going to be higher at cruise RPM than it's going to be at idle RPM. Let's assume that you use a lubricant that the manufacturer has recommended for a much lower temperature. What's likely to happen? You're going to have oil pressure being lower than normal, because if you use a lubricant that the manufacturer said use for a temperature much lower than what you're actually operating in, you're going to have an oil that doesn't have the thickness, the viscosity you need for your higher temperature, and that's going to give you a lower than normal oil pressure, or at least it could possibly. Now, what if the oil pressure gauge fluctuates over a wide range from 0 to normal operating pressure? What kind of thing could cause that? The most likely cause of a fluctuating oil pressure gauge is low oil supply. Now, low oil pressure can be detrimental to the internal engine components, but high oil pressure is not desirable either. High oil pressure should be limited to whatever the manufacturer recommends. Now, let's talk about turbine engines and the lubrication system in turbine engines. First of all, manufacturers normally require that if you're going to service the engine oil, check the oil and see if it needs adding or not, you have to do it within a very short time after engine shutdown in order to prevent over-servicing. By over-servicing, we mean overfilling. So you usually have to check it within about 10 to 15 minutes after shutdown if you're going to get an accurate indication of the oil level in order to prevent over-servicing, which means overfilling. Now, the type of oil system that turbojet engines normally have is a dry sump system with pressure and spray lubrication. So you've got a dry sump system, and you're also going to have oil that is applied using both pressure and spray lubrication systems. A turbine engine dry sump system, that is self-contained and high-pressure design has some subsystems to it. And those subsystems that it has are the pressure, the breather, and the scavenge subsystems in that lubrication systems. Now, the main bearing oil seals that are used with turbine engines may be the labyrinth type, as the JT15D engine has got, and another type that you might see is carbon rubbing type. So the main bearing oil seals for turbine engines will usually be a labyrinth or a carbon rubbing type. Now, the main bearing oil damper compartments that some turbine engines have are used primarily to provide an oil film between the outer race and the bearing housing, and that reduces vibration tendencies in the rotor system. Most turbine engine oil tanks incorporate a relief valve, a check relief valve in the tank venting system. And the purpose of that check relief valve is to prevent oil pump cavitation. And the way it does that is by maintaining a constant pressure on the oil pump inlet so it doesn't end up pulling air in. Now, the reason that the oil tanks of most turbine engines are slightly pressurized, the reason is to ensure a positive flow of oil back to the engine. Now, what type of oil pumps are most commonly used on turbine engines? The most common type of oil pumps are those classified as positive displacement oil pumps, pumps like the gear type pumps that provide positive displacement. In the lubrication system on a gas turbine engine, they use fixed orifice nozzles, and the purpose of using those fixed orifice nozzles is to provide a relatively constant oil flow to the main bearings at all engine speeds. So the fixed orifice nozzles are to give a constant supply, constant oil flow to the main bearings regardless of what the engine speed is. Now, the primary purpose of the oil breather pressurization system on turbine engines is to provide a proper oil spray pattern from the main bearing oil jets. So they pressurize the breather system, the oil breather system on turbine engines to help provide a proper oil spray pattern from the main bearing oil jets. The gears, the teeth of the gears in the accessory section of an engine, how are they normally lubricated? They're normally lubricated by splashed or sprayed oil as opposed to pressure oil. Splashed or sprayed oil as opposed to pressure oil. Now, the air and the oil in a jet engine oil system need to be separated at the end of the cycle, and the way they do that is by returning the scavenged oil to a unit called a de-aerator at the top of the oil reservoir. The de-aerator simply means to get rid of the air, and it's getting the air out of the oil when it's returned into the top of the oil reservoir. Now, jet engines can be of either the dry sump or the wet sump system. Let's talk about the wet sump system. They're not real common on in-flight aircraft engines, used a lot for APUs and so on, but they will be asking you some questions about it as far as a wet sump turbine engine system is concerned. One of the things you need to be aware of is that oil coolers are not used on turbine engines that have a wet sump lubrication system, and the reason for that is because cooling air is directed to the turbine wheel and to the turbine bearings to carry away the heat. Now, where does the oil get the most heat from in a turbine engine? It gets the most heat from the turbine bearing. In an axial flow turbine engine, one of the things they do is they use compressor bleed air sometimes to help in cooling the turbine and the turbine bearing. So by using compressor bleed air to cool the turbine and the turbine bearing, then there is less heat there for the oil to have to pick up and carry away. So bleed air directed to the bearings on turbine engines eliminates the need for an oil cooler in a wet sump lubrication system. But how about a dry sump system? Well, turbine engines that depend solely on the lubrication oil for bearing cooling, those kinds of engines normally will use an oil cooler in the system. Now, how are you going to cool that oil? You could cool the oil with fuel. You could cool it with ram air. Both of those are used in gas turbine engines, both fuel and ram air coolers. Let's talk about cooling it with fuel. Let's talk about a fuel-to-oil heat exchanger. Now, if you've got a jet engine which does use a fuel-to-oil heat exchanger, basically, the oil temperature is controlled by a thermostatic valve that regulates the flow of oil through the heat exchanger. In other words, how much oil goes through this heat exchanger is regulated by a thermostatic valve. What you're looking at here is the blue is the fuel that's flowing through this piping, and then the red is the hot oil coming in through the system around and inside the fuel, in tubes inside the fuel, and then you've got the cooled off oil that is exiting and continuing on to the engine. One of the things that's going to happen, one of the functions of the fuel oil heat exchanger is that you will get an increased fuel temperature. Because here you are running cool fuel in, but then you're running hot engine oil through that fuel. When that engine oil gets cooled off, what's going to get heated up in return? The fuel is going to get heated up. So you will get increased fuel temperature. That's not the primary purpose of this fuel oil heat exchanger, but it is a byproduct, it is a function that you get an increased fuel temperature. The primary purpose of the oil to fuel heat exchanger is cooling the oil. It's cooling the oil, not cooling the fuel or heating the fuel or doing all kinds of other things that they might throw at you. And it's not all that easy to keep straight because they call it a fuel oil heat exchanger, an oil fuel heat exchanger, but the primary purpose of the unit, whatever they call it, is to cool the oil for that aircraft engine. Now, the oil temperature indicator on a gas turbine engine is going to indicate the oil temperature as the oil leaves the oil cooler. That's where the oil temperature indicator on a gas turbine engine is picking up its indication. It's as the oil leaves the oil cooler. Now, let's talk about cooling the engine itself as far as the combustion chamber is concerned. There's two types of air that pass through the combustion chamber of a jet engine. You've got primary air and secondary air. The primary air is used to support combustion, and that means basically it's burning. That's the air that's being used in the combustion process. But you also have secondary air, and the secondary air is used to cool the engine. So through different holes, different areas in the combustion chamber, you introduce both primary air for combustion and secondary air to cool the engine. So the combustion liner walls in a gas turbine engine, the liner walls of the combustion chamber are cooled by secondary air flowing through the combustion chamber, because the purpose of that secondary air is to help in cooling the engine. Now, on some engines, bleed air is used to control the temperature of the outer turbine case. By using the bleed air to control the temperature, you can have optimum turbine blade tip clearance. You're controlling the thermal expansion of the case so that the blades clear the case, but just barely, and that way you don't lose any thrust out of the engine, and you do that with bleed air to the outer turbine case. One way to protect the health of a turbine engine is through the use of chip detectors. Chip detectors are designed to detect magnetic or metallic particles in the turbine engine oil. With a chip detector, what you have is a detector center electrode, a positive electrode, and you also have a ground electrode. And when you have metallic particles in the oil, what happens, the way this works is that those particles will bridge the gap between the center and the ground electrodes, and that will light a chip light in the cockpit and tell you that the chip detector is detecting metallic particles in the oil. Now, as a general rule, a small amount of small fuzzy particles or gray metallic paste on a magnetic chip detector is considered to be the result of normal wear. What you don't want to have is larger metallic chips that give an indication of some kind of abnormal wear in the engine. Now, another way to protect the health of the engine is an oil analysis program. A turbine engine oil analysis program is very useful because what it does is it gives you an idea of the trend of the engine, how much metal of various types is in it and in the oil, and what that tells you about the health of the engine. Now, a turbine engine oil analysis program will not be able to forecast accurate trends after just the first oil sample, because what it needs is a number of oil samples in order to project lines out and tell you whether the wear in the engine is normal or abnormal. If you really want a successful oil analysis program, the program should start when the engine is new. It can be reasonably effective if it's started anywhere in the engine life, though, if it's run over the total engine operating life. What you do not get with the program, though, is accurate information, accurate trends after the first oil sample. Now let's talk about reciprocating engines. And let's talk about lubrication specifically for reciprocating engines. First of all, they're going to be throwing some questions at you about radial engines. The primary source of oil contamination in a normally operating radial engine is combustion deposits due to combustion chamber blow-by and also due to oil migration on the cylinder walls. Now, most of the heat which is absorbed by lubricating oil in an aircraft engine is from the pistons and the cylinder walls. So where your heat is coming from, which gets absorbed by the lubricating oil, is from the pistons and from the cylinder walls in a reciprocating aircraft engine. The cylinder walls are usually lubricated by splashed or sprayed oil. So the cylinder walls will have oil splashed on them or sprayed on them. The way you keep excessive oil from accumulating on the cylinder walls is because the pistons have oil control rings on them, and those oil control rings scrape the excess oil off of the cylinder walls. One of the things that means is if you've got a high-powered engine and it's been ground operated at high power and it's gotten up to high operating temperatures, you as a mechanic, normally you'd be doing this to run up and check something that you were trying to fix. You as a mechanic should be careful not to decelerate the engine too quickly, because what you can do is you can carbonize the oil that is trapped in the ring grooves, and you don't want to do that. So if you've got a high-powered engine that you've run at high power and the temperatures have gotten up there, you want to decelerate the engine slowly. Don't decelerate it too quickly, because you could carbonize the oil that's trapped in the ring grooves if you do that. Now, that piston oil control ring collects the oil off the cylinder walls, and it returns it through to the crankcase through holes that are drilled in the piston oil ring groove. So the holes in that oil ring groove will let the oil that it collects off of the cylinder walls return to the crankcase. Let's assume that you've got an inverted engine, or you're looking at the lower cylinders of radial engines. How do you prevent oil accumulation in the cylinders? Because what would happen if you didn't have something to prevent it is that the oil would run down around the crankcase and then just simply run down into those bottom or inverted cylinders. The way you prevent that oil accumulation is by extended cylinder skirts. These little projections sticking up here are the extended cylinder skirts. And basically all it means is that the cylinder looks like the bottom end of it, which is actually the top as you're seeing it here, but it's what's sticking up into the crankcase. That area basically is like a standpipe that sticks up into the crankcase a ways, so that oil that does move around the crankcase will be caught between the wall of the crankcase and that cylinder wall, and it will be prevented from just going right on down into the cylinder itself. So those extended cylinder skirts are what prevent oil accumulation in the bottom cylinders of a radial engine, or if you have an inverted engine. Now, looking again at our cylinder, let's talk about how the piston pins on most aircraft engines are lubricated. And they're lubricated, the piston pins are, by oil which is either sprayed or thrown by the master or connecting rod. But some areas have to have pressure lubrication. For instance, plain bearings. If you have plain bearings, as you often do in the crankshaft, plain bearings have to be continuously lubricated by pressure oil. Now, looking at the crankshaft, sludge chambers are usually located in the crankshaft throws, and those sludge chambers will accumulate sludge in the aircraft engine, and you have to be careful with them if you do an overhaul on that engine. But where they're located usually is in the crankshaft throws. Now, if you've got an aircraft engine that's used in a helicopter, the overhead valve assemblies of reciprocating engines used in helicopters have to be lubricated by means of a pressure system. So the overhead valve assemblies of opposed engines used in helicopters will have a pressure system of lubrication. If you happen to have a plugged crankcase breather, what's that going to cause? Well, a plugged crankcase breather could cause excessive pressure in the crankcase of a reciprocating engine. One of the questions they're going to be asking you is about where the oil temperature indication is taken. The oil temperature indication, if it's in a dry sump reciprocating engine, will be located in the oil inlet line. If it's in a wet sump reciprocating engine, it will be sensing the oil temperature after the oil has passed through the oil cooler. So there's a difference on where the oil temperature is taken, depending on whether it's a reciprocating or turbine engine and whether it's dry sump or wet sump. Now, one of the things you typically find when you have a vacuum pump, and of course when you have a vacuum pump, you've got a vacuum gauge that tells you how that pump is performing. But when you've got an engine-driven vacuum pump, you're generally going to have an oil separator in order to get rid of any oil that might try and get into that system. So an oil separator, the unit that an oil separator is generally associated with, is an engine-driven vacuum pump. Now let's talk about engine cooling for a little bit. Let's assume that you've got an aircraft engine that's gotten overheated because you've been taxiing too much or a lot of ground run-up. What should you do? Before shutdown, continue running until the cylinders have cooled by running the engine at idle RPM. If that engine gets overheated before you shut it down, idle it for a while in order to let those cylinders cool off. Most of the heat, the greatest portion of the heat that is generated by combustion in a typical reciprocating engine goes out with the exhaust gases. It's about half of the heat that comes out of the engine, and it's carried out with the exhaust gases. And a lot of the rest of that heat, the oil has got to try and cope with. Now, if you've got a radial engine, a twin-row radial engine, what they do with the cylinders on a twin-row radial engine is they stagger them with respect to each other, and the purpose of that is to facilitate cooling, because by staggering them, the cylinders are more exposed to the airflow in that twin-row radial, and they're going to be cooled better by the air. If you've got a reciprocating engine that's used in a helicopter, because of the fact that helicopters very frequently don't have much forward speed and the rotor doesn't produce the right kind of airflow for much cooling, the reciprocating engines used in helicopters are normally cooled by a fan that's mounted on the engine. So you'll have a fan mounted on the engine to cool that helicopter engine. Reciprocating engines can also be cooled by fuel. Excess fuel over what you need for combustion will help cool the engine. And if the reciprocating engine is operating at or near takeoff power, the mixture setting that you want that's going to provide the best cooling is full rich, full forward on that mixture. That will give some excess fuel that will be available to help cool the engine. Now let's take a look inside the cowl and talk about baffles on the aircraft engine. A baffle and cowl arrangement helps to remove heat from the metal walls and fins of an air-cooled cylinder assembly. And the baffles are this material here around the front of the engine and also between the cylinders and around the cylinders, and they'll be across the top of the engine. And by the way that the baffles and the cowl meet each other, it controls the airflow and it helps in removing heat from the walls and the fins of the cylinder assemblies. The whole idea of those baffles and the deflectors is to force cooling air into close contact with all parts of the cylinder, because the whole idea is to get a lot of cool air moving around those cylinders in order to carry away the heat. So in order to keep the cooling working properly on the engine, to prevent loss of cooling, the cylinder baffles and deflectors should be repaired as required. Now, let's assume that you've got a small crack that's just started in a cylinder baffle. Do you have to just throw away the baffle? No, you don't. Generally, a small crack that's just started generally can be stop drilled. Now, attached to those baffles a lot of times will be blast tubes, which are basically just tubes that direct the air, because those baffles are directing the air and the tube will focus it a little bit more. And the blast tubes will focus air to cool an engine accessory, or it might be under the spark plug elbows or something like that. So the primary function of the blast tubes on aircraft engines is to cool an engine accessory. The purpose of cooling fins on an air-cooled aircraft engine is to dissipate the heat that is generated in various locations by that engine. So where are the cooling fans usually located? You'll find them on the cylinder head, the cylinder barrel, and inside the piston head. What you're trying to accomplish with the cooling fins is you're trying to conduct the heat from the inside of a cylinder barrel out to the cooling air so the air can cool that cylinder off. The most common way and the best way to do that is to machine the fins directly on the outside of the barrel. The distinction that the FAA is drawing here is that machining the fins directly on the outside of the barrel, where it's out of the same material, the same case, is going to provide better cooling than a jacket that has cooling fins on it, a jacket that goes around the barrel that is of a different metal. So the best way, the most common way, and the best conducting way to do the cooling fins is to machine those fins directly on the outside of the cylinder barrel. Now, what if your cooling fins are not in perfect condition? A bent cooling fin should be left alone as long as there's no crack. Trying to straighten that fin, you're likely to damage it. A bent cooling fin has not lost any of its heat dissipating area, so it's no big deal. Just leave it alone as long as there's no cracks. What if you have a broken cooling fin instead? Broken cooling fins can be filed down to smooth contours provided the damage or repair limits are not exceeded. So you need to make sure and check so that you don't exceed the damage or repair limits. If too much cooling fin area is broken off, what you're likely to get out of that, what it's likely to cause, is a hot spot in the cylinder. Now suppose that you have cracks in the cooling fins. As long as they do not extend into the cylinder head, they can be repaired by removing the affected area and contour filing to smooth it down, again, as long as you stay within the limits. So how do you determine the maximum amount of the fin that can be removed when you're filing down, when you're reprofiling that fin? What you should do is consult the engine manufacturer's service or overhaul manual. You can never go wrong by consulting the manufacturer's service or overhaul manual. Now, another way to help control the cooling on an aircraft engine, particularly a horizontally opposed aircraft engine like we've got in the Mooney, is cowl flaps. Here are the cowl flaps on the Mooney. They are in the open position right now. When they're closed, this will be tucked up flush against the belly of the aircraft. When they're in the open position, as they are now, a lot of airflow can come in the intake up here and move around the cylinders in the aircraft, and then it comes out through here. If the cowl flaps are closed, it doesn't allow as much air to come in the air intake and to flow around the cylinders, and therefore when the cowl flaps are closed, you do not get as much cooling. The air, by the way, is flowing around the cylinders. It is not flowing through the cylinders. So the cowl flaps help to control the cooling by controlling the amount of air that is flowing around the cylinders, depending on whether the cowl flaps are open. In that case, you get a lot of cooling airflow around the cylinders. If they're in the closed position, you get very little cooling airflow. Let's take a look now at a Cessna 340 and talk about how we want those cowl flaps to be set. Basically, what you're concerned with is you want the cowl flaps to be open, as they are here, whenever you don't have a pretty good airflow through the engine, and particularly when you're operating at high power settings, because the engine will tend to get really hot then. So when do you want the cowl flaps open under normal conditions? You want them open for engine starting, for warm-up, and for taxi, basically for all your ground operations, and for takeoff and climb, because you're operating at pretty high power and the engine will tend to get hot because you don't have a good airflow through it. So when do you want the cowl flaps closed? Basically whenever you've got a lot of airflow through the engine, and particularly if you're operating at a low power setting. So you would want the cowl flaps closed during normal cruise operations, and also on descent, because you'll normally have the power back and you'll still have a pretty good flow of air through those engines. Now, some aircraft have an electrically powered radial engine cowl flap system. In this particular case, we're looking at a Corsair that has a hydraulically powered cowl flap system. But if you did have an electrically powered cowl flap system, the FAA wants you to know that if the motor fails to operate, the first thing you want to do is check the circuit breaker. What you would do is check the cowl flap actuator motor circuit breaker first in order to see if you can get the system working, if it's an electrically powered cowl flap system, as some aircraft do have. Now, on some aircraft engines, you're going to find augmenter tubes. The purpose of an augmenter tube on a reciprocating engine exhaust system is to help in cooling the engine, and here's how it does it. You've got the exhaust coming out of the engine on each side here, and basically what the exhaust does is act as kind of a venturi. It goes through this augmenter tube right here, and as the hot pencil form of exhaust gas goes through there, it pulls along with it masses of air from the general engine and cowling area of the engine. What it's basically doing is creating a low pressure area which pulls air into it, and by pulling air into these augmenter tubes, it pulls more air through the engine, and that helps cool the engine. So the purpose of an augmenter, and they call it an augmenter instead of augmenter tubes, although augmenter tubes is a very common terminology. The purpose of an augmenter on a reciprocating engine exhaust system is to help cool the engine.